Good morning from whichever part of the world you're calling in from. Thank you for joining this presentation. As Louis did a generous introduction, thank you very much, Louis. I've known Louis for the last, 25 years. We started working together, Intel analog devices, joint development. The X scale that you see here, that's the product that we worked on. We had a cell phone chip way back in 2000, going to the crackberry, as they say, BlackBerry, right? BlackBerry, people used to be so addicted to it. And then iPhone came and totally killed, right? Is this being recorded? Is this being recorded?
Yes.
Oh, it's being recorded. So I got to be careful what I say. Okay.
Say anything bad about BlackBerry, but you can say bad things about Apple.
You're on the tape, Louis. No, just kidding. Just kidding. Okay. Thank you. So I will try to stay on track. And I chose the topic system and platform debug using the ubiquitous USB Type-C connector. And I looked up what ubiquitous stands for. It is existing or being everywhere at the same time. And I guess the USB Type-C has become a connector that you see everywhere, right? You must have heard about European Union said that unless your device has USB for power, we will not accept it. So everybody moved to USB-C for power.
It's on the screen.
Until then, you had different bricks, different connectors. I remember I had a Dell laptop and I forgot my brick. And I looked around everywhere. I couldn't find I tried the HP, it wouldn't work. I tried different ones. I had to get the Dell for that particular model, right? So thankfully, that has been resolved now. Everything eventually will be USB-C. And I was fortunate to work on the USB-C standards along with MIPI and IEEE. So I'll talk to you all about it and how USB came about from 1994, right? That was like 30 years ago, 40 years ago, something like that. So let me start off. What's the outline of my presentation? I want to talk about, since debug is the main topic today, I want to talk about, I would like to compare debug with detectives and with medicine, right? And I'm going to talk about what is system debug versus platform debug. It's essentially, it's not just hardware debug, it's hardware, software, and firmware debug. And I'm going to talk about open chassis and closed chassis. And I'll give you a brief history of USB, as I just mentioned. And the most choicest connector for closed chassis and in-field debug, I'll talk about in-field debug in a minute, is Type-C connector. The reason why the debug connector is Type-C is because we went to the vendors, we went to Dell and HP and said, hey, can you give me a connector for debug purposes, right? And they said, take a hike, right? Because the connector is going to cost me $1. And we make probably 500 million, PCs are sold, 300 million PCs or 500 million PCs. Times, even if it's $1, that's a lot of money, right? So they said, no, try to repurpose an existing connector for debug purposes. And we said, what best choice other than USB-C? So we worked with the MIPI group, which is a mobile group for coming up with connectors, small connectors on phones. So came up with a capability using closed chassis and for in-field debug. And then I'm going to talk a little bit of usage of this for in-field verification and validation, as well as for silicon lifecycle management. And then I'll talk about future platforms. So one of the things that I did was work on wireless debug. So what prompted me to work on wireless debug is that very often these days, we pick up a Bluetooth headphone, we connect it to ears, and then turn on, and then we're able to listen to music, and you have mouse which works through Bluetooth. I said, if you can use all those devices, why not I do debug wirelessly, right? All you need to do is pair it and then make sure the security is taken care of. And we did demonstrate Bluetooth-based debug, and it's being used currently. And the next step that we are working on is Wi-Fi-based debug, right? Connect through Wi-Fi. As long as you take care of security, you should be able to debug. So moving on, I want to talk about why debug? It's for hardware, software, and firmware debug. We'll address the hardware debug first. Hardware debug, there are three main different types. One is first silicon that you receive from the fab. So when you receive silicon from the fab, you send the design, the GDS2 from the design house, and it goes to TSMC or Intel or Global Foundries or Samsung, and then you get the silicon back, and you expect the silicon to work the very first time, right? Surprise, surprise. It takes about a few months to debug it. And it could be a surprise, right? It could be a PLL problem. It could be a CPU problem. It could be anything. And if you can shorten the debug time and launch the product a week or two early, you can be first in the market, right? And then you can make all the cha-ching, the money that you can think of. So people think that, hey, adding debug structures is actually wasting space. It's actually not. You can reduce the time, you can make money, right? And we have quantified the amount of money saving by adding debug capability. So one is the first silicon that comes into the lab. Second is the hardware debug of system failures. So once the laptop or computers or devices are launched, now you could have a sudden failure of the system, right? And that's what is the second category. And the third is we being a company being Intel or AMD or NVIDIA, they could get the return parts back. When you get the return parts back, you want to find out what is causing the failure, because it could be a systematic issue, a systemic issue, which is probably happening to a particular lot, or it could be happening to every device, or it could be a random. So you need to study that to find out what is causing it. So it's very important to be able to root cause and find out what is wrong. It could be a software bug. It could be a firmware bug, right? Now, why does a first silicon have these errors? It could be because when you look at silicon, silicon has inherent defects, right? And the defect could be clustered, it could be spread, and wherever there is a defect, it could be with the impurities due to mask issue, due to scratches, due to dust particles. You see people, Intel has this ad about people in bunny suit. The reason why they wear bunny suit is not because they want to look like bunnies. It's to make sure that any dust particles that they carry from outside doesn't contaminate the silicon, right? So it could be dust particle. And imagine the chips that are being made, the feature size is 3 nanometer, moving to 1.8 nanometer. Our hair size is like much, much thicker, 100 times thicker than 3 nanometer. So a hair particle falling can actually destroy hundreds of chips, right? So you got to be extremely careful. And if you look at faults, are incorrect state of hardware or software resulting from a physical defect. An error is a manifestation of a fault. Imagine a SRAM bit being 0 instead of a 1. That's an error. And these errors cause failures in the system, like a system hang. Now, while you're working, suddenly you see blue screen of death. And it could be due to many, many reasons. It could be hardware, it could be software, it could be firmware. And all these failures need to be debugged to release the product to the customer. So you have defects causing faults, faults causing errors, errors causing failures. Now, moving on, I wanted to bring some parallel between the SoC or chiplet debug system or platform debug with what a detective does. It's essentially what we do in the lab is nothing but what a detective does or a doctor does in medicine. So if you look at what detectives do, they are looking for clues to solve the problem. And in medicine, doctors look for clues by examining patients. Now, let's see. There are non-intrusive ways of medicine, right? And you have intrusive ways. Intrusive is like surgery. Non-intrusive is touch and feel, stethoscope, X-ray imaging, MRI, PET scan, EKG, EEG, right? And if you go to intrusive, it's laparoscopy, surgery, and then you have these remote surgical instruments called Da Vinci. Now, you have equivalent in the chip world. Touch feel is like connecting a debugger. Stethoscope is connecting a debugger and doing control. X-ray imaging is like scan observability, array observability. And if you look at EEG, ECG, it's like trace, right? You're getting continuous trace, continuous glucose monitoring, right? Which is nothing but all you have to do is just map it on your laptop. Bluetooth message keeps sending. It's nothing but tracing, right? And so essentially, what we do is similar to what doctors and detectives do, right? We're trying to find the root cause as to what is causing a bug, which is what is debugging. And in case of surgery and laparoscopy, it is modifying the memory contents. Or the biggest is FIB, right? If all else fails, there is no way you can debug it non-intrusively. Then you take it to a lab, you do microsurgery, just like doctors do surgery. We delid the chip, we expose the chip, we mill it, we go and find out what is potentially wrong. Moving on, process of debugging, we try to reproduce the bug, locate the bug, root cause the bug, find a fix, make sure that the fix works, and then you document it so that the next set of people can learn from it. And the way it is detected is you see the bug, right? And then you are debugging it, as you can see over here. And then if you look at the bottom left side, you see the target system. Target system is the system that you're trying to test. On the right-hand side is the debug and test system, which is what is the debugger. The debugger is what says, oh, give me register R5 value, register R10, send me trace, right? And then the debugger will actually capture the information, and you sit in front of the debugger and debug and find out what exactly caused the problem. Moving on to the next foil. What is the difference between system and platform? On the right-hand side at the top is a system. A system is nothing but a board. A board comprises of several SoCs. It could be chiplets. It could be SIPs or SoCs. SoCs you're familiar with, system on chip. SIP is silicon in package. And so as I showed earlier, in the bottom left side, you see the target system that is being debugged, or it's also known as DUT, which is device under test. And the debugger is connected, and what is connected using a JTAG port. JTAG is a very common IEEE 1149.1 port, which is essentially 4 wires. You have clock, TDI, TDO, TMS, TCK, and it actually sends signals back and forth. You can ask the device and say, hey, send me the register value, and you can get the information. Now, platform is made of several of these systems connected together in a box. In the bottom, you can see there are different, it could be a smartphone, it could be a laptop, it could be a server, right? So platform consists of several boards assembled together. Could be laptop, server, smartphones. Typically, debug of platforms are done by unscrewing it, removing the board, and connecting it. And it takes about 15, 20 minutes to unscrew. If you look at the bottom of this laptop, you'll have about 8 screws. Imagine try removing it. It takes about 15, 20 minutes. Then you take the board, you connect the JTAG connector, and you start debugging. It'll take you probably an hour or two by the time you connect the debugger for debugging it. Now, all that is history. What we've done is we came up with a way by which you can use the existing Type-C connector that you see in the box here, which is connected to the monitor. By connecting the debugger, you don't have to open the box up. So it's a big savings of time, and it's convenient, very, very convenient. So it saves a lot of time. Moving to the next foil, types of debug. For silicon, as I mentioned, and sometimes it could be due to the system not booting. It could be dead on arrival, right? In human beings or in medicine, if something is dead on arrival, there is no way to revive it other than post-mortem, right? You study and find out what caused it. We also do post-mortem. We don't call it post-mortem. We call it as debug. We want to find out why did a system fail so that the next system can be fixed. We can avoid the same problem by perhaps sending a over-the-air firmware update, right? So if you have a Tesla car or your phone, you'll suddenly see that, hey, there is an update available. Do you want to update it? And you say, schedule it for tomorrow night, right? So some of these updates are so critical that you may want to do it immediately because there are some security issues that they're fixing, right? So dead on arrival is in case of chips, we want to do investigate and find out what is causing it. And hardware debug of system failures, it could be because of marginal degradation or transistor degradation, or it could be aging related. Let's say the system, most of the electronic systems are designed to work for about 7 to 10 years, whereas automobile is even longer. because automobile and space applications have much, much longer life. They have much higher tolerance. So what happens is with time, your clock could drift, your duty cycle could drift. Any of those could cause degradation. And then you have debug of return paths, right? It's called RMA, return material authorization. And these could be some catastrophic failure, it could be temperature related, and those all need to be debugged. And debug is absolutely important. Now, I'd like to shift gears and talk about, this is my favorite topic, talking about history of USB. USB, as you know, it stands for Universal Serial Bus. And it actually evolved over time. It's been about 20 to 30 years or so. The first USB was invented at Intel by Ajay Bhatt. I know Ajay Bhatt. It's along with Microsoft, LSI, and Apple. Intel said, hey, let's have a common connector, which can be used for data transfer, right? It started off as data transfer, 12 megabits per second. Nothing to sneeze at during those days. 12 megabits was really, really fast when the processor used to run at 10 megahertz or 25 megahertz. And I remember when I was in school, people used to say that CMOS, you'll be lucky if it works beyond 25 megahertz, right? And boy, am I surprised, right? Silicon runs at gigahertz now. And then the biggest advantage of USB was hot plug capability. Every other connector, you had to power it down, connect it, power it back up. And booting, you know how long it takes, right? So hot plug was amazing, right? You connect it, it enumerates, it knows what you've connected, whether a printer or a camera or whatever, right? A human being, no, not yet. Human beings are not there yet. Well, I did see a Spectrum magazine a few years back with a connector at the back of a person's head. And it said, year 2040, the year man becomes immortal, right? And you have a connector connected. Maybe that's what is Elon Musk trying to Neuralink, right? Neuralink might be the solution to man becoming immortal. Who knows, right? You might need an update once in a while. I always think, that there should be a connector in a human body, which you download and take it to a debugger and should tell you what disease you have, right? USB-C connector would be nice. I'm sorry? Exactly, the umbilical cord, right? They cut it off. They shouldn't. Okay. And then came USB 2.0, right? Which it came in 2000. And that was another leap forward. It was self-powering. It was plug and play. It was backward compatible. And it was on the go. On the go. I'll talk a little bit more about what on the go is. And then moved to USB 3.0 in 2008. It had 5 gigabits per second. Oh my gosh. And then 3.1 revolutionized it, went to 10 gigabits per second. 3.2 became 10. USB 4 came out in 2019, is 20 gigabits. And now it is USB 4, 2.0 at 80 gigabits. It also is symmetric, 120 and 40 gigabits per second, 2 lanes. And now if you look at, there's another connection like USB. Intel has their own proprietary called Thunderbolt, which is being used in Apple, and some of the devices are using it. And originally, Thunderbolt was supposed to be on fiber, but then it's available on silicon now, almost 80 gigabits per second. So USB 4 also is available on Thunderbolt, I was told. I need to double check. So open chassis debug is when SoC is installed on a board, typically validation board and debugging performed using a debug connector like JTAG or a serial wire debug. Serial wire debug is ARM's way of debugging, right? So they essentially wanted to have a single wire debug, but decided to call it serial wire because you need a data and clock. So the advantage of open chassis is that most pins are accessible in an open chassis. Now, the biggest advantage of a closed chassis is that so system could work when you're in open chassis because it's open. You have very good thermal effects. You have air cooling, and RF effects are not there. The moment you put in a box, the whole characteristics changes. It becomes very hot. The thermal effects, the RF effects are very different. So now if I can debug in its native way using a closed chassis connector, that would be the best. Now, one other thing that moving on to USB, if you see the connector, it is directional, right? If you look at type A, USB type A, there's an upside down and downside up. Now, even though there are odds of connecting is 50%, I've seen odds of connecting it wrong is definitely more than 50%. Every time I pick cable and connect to US type A, it's wrong. How come? I should get at least 50% of the time I should get it right? No. So that's why type C is very, very advantageous. If you look at type C, in the middle of the night, I forgot to charge, I get half asleep, I can take off my phone and connect it, it'll go the right way, right? Because now it's not because you're connecting it right, it's not because it's made correctly, it's because all the smarts are built inside. The smarts are built inside. I'll show you how a USB type C. Once you see that, you'll say, oh my goodness, didn't expect it to be like that. So here are the USB connectors. Now, I want to talk a little bit about type A and type B connector. Type A's are the ones which is host. Your laptop is a host. Now, your printer, the connector on that side is different, right? It's not the host, it is a device, right? So host and device. So device has a different connector. You can't interchange. Whereas type C is host and device are exactly the same, right? So now how does it know who's host, who's device? Negotiation. Exactly. So you negotiate, they both negotiate and say, you know what? I'm going to be host. They say, no, I want to be host. And then you can change it, right? With the help of a driver, you can change it. So the biggest advantage is you're never upside down. You're always the right way, right? And then there's something known as USB PD, power delivery. You can take the power up to 240 watts of power. It can go up to 48 volts at 5 amps. Now, type A, if you refer, it was at 5 volts. And as I mentioned, USB 3.2 Gen 1 supported 5 and 10, 3.2 supported 20, moved out to 40, and then USB 4 V2 is 80 and 120 and 4 gigabits, 40 gigabits per second. Now, Thunderbolt is supported over USB-C up to 40 gigabits per second, 2 lanes, or 80 gigabits, 1 lane. Now, if you look at the connector itself is very, very thin compared to type A, right? It's very tiny and still provides 240 watts of power. It's versatile, it transfers data, and it charges and powers both. It can work as a video port. It hooks to external display. And Louis and I were talking, what they found out on the cell phones was that the biggest connector on a cell phone, the vendors found, is the 3.5 millimeter audio jack. If I can avoid and get rid of that, there's a big real estate saving on a phone device. So if you see, everything is overloaded on your USB-C. You have a dongle coming out, right? From the dongle, you can connect a headset. From the dongle, you can connect to USB 2. Dongle, you can connect to USB 3. From the dongle, you can connect to display. You can connect to HDMI. And in addition to that, we worked with the USB standards and said, hey, why not we use this for debug? They said, sure, if you can solve the debug problem, do it yourself. So we all sat together, a group of people, and said, let's come up with a debug methodology. We call it as USB debug class. And I'll talk about it. And that's what makes USB-C ubiquitous, right? It's bidirectional, and it's a single connector, as you can see here. Most devices have just one connector. In my case, I have two, one for power, one for display, right? So it actually saves a lot of real estate and helps a great deal. Now, what is inside it that makes it smart? Now, here it is. It's becoming an ubiquitous connector in present day and future devices used for charging, power, keyboard, mouse, display, audio, debug as well, right? So here's the pinout of USB Type-C, even though it's a tiny connector. So look at the symmetry, right? Look at the edges. On either of the edges, you have ground. So you connect it this way or this way, you get ground correctly, right? And look at where the V bus is. V bus is fourth from the right or left. You connect it this way or that way, you're perfect. Look at the D plus D minus. You flip it, the USB 2 will be perfect, right? Symmetrical. Now, what is different is the TX1 plus, TX1 minus, and RX1 minus, RX1 plus, and the corresponding TX2. Now, what these mean are TX1 and 2 are differential USB 3 pair. One is for transmit, the other is for receive. So you have two sets of USB 3, receive and transmit. Now, when you flip it, you don't know which is 1 and which is 2. How do you know that? You see a pin called CC1, CC2. That's called channel configuration pins. So channel configuration pins tells me, aha, my TX1 is on the left side, TX2 is on the right side. Flip it, it'll tell you it's on this side, that's it. Now, I can combine TX1, RX1, TX2, RX2 to form HDMI. You need 4 lanes, right? So either get 2 sets of USB 3.1 or 3.0, or you get a display, or you get display, right? So HDMI. So, and now when you go into debug mode, so let me build the animation. So that's the Type-C connector, that's USB high speed. High speed is nothing but 2.0. Then you have USB super speed, which is USB 3. Now you see 2 pins called SBU. Those are called sideband usage. So, so the USB consortium said, we have these 2 pins. What do we use it for? We can use it for headset, right? This is for headset. Or then some people said, you know what? I want to use it for signaling sideband. Sure. We said, I want to use it for bare metal debug. So we use that for bare metal debug. So now, suddenly, this has become best thing since sliced bread.
So it's
right?
similar to GPIO, like
Exactly. It's similar to GPIO. Yeah. Yeah. GPIO is like 200, 300 megahertz, and this can even go higher. So USB-C can be used for many purposes, USB 2, USB 3, display, audio, right? And now we said we're going to use it for debug. So this makes it multi-purpose and the most ubiquitous connector in the world, right? I was so fortunate to work on this and, you know, provide my 2 cents worth to contribute to the standard. So my name is there on the standard, which is very good for posterity. I can go back and look at my name and it's there. Now, moving on, I want to shift gears and talk about open chassis and closed chassis. How are we doing on time, Lois? Are we okay?
We have until 7:30.
7:30?
How many slides we have?
I probably have, I think I'm probably 1/3. I've got 2/3 to go.
Okay.
Yeah.
If you can speed up.
Speed up a little bit. Okay, sure. I'm halfway there. Okay, good.
time-wise.
Okay, time-wise, I have 45 minutes. But I'm not halfway with my spoils. Okay. Yeah, I like to take time to explain things, so it becomes easy. I'll probably speed up. So look at open chassis debug. Open chassis is, as I said, on the left-hand side, you have the TS, which is a board that you're trying to debug. And the extreme left, you have DTS, which is debug and test system. It's connected through a JTAG interface, and you're debugging it. And closed chassis, on the right-hand side, you see a smartphone, a laptop, a desktop, and a tablet connected to a DTS. And the connection is using a closed chassis interface, which in our case, it is USB Type-C. Now, as I mentioned before, in a closed chassis, what happens is that the RF is different, the temperature is different, it could become hot, and things might not fail in open chassis, but it could fail in closed chassis, right? So all that you are actually testing in its native behavior, right? That's why everybody prefers closed chassis. And ever since closed chassis came, people have been using closed chassis. But things have not been easy to come up with closed chassis, and I'll explain to you. Extreme left is the open chassis, right, which is also called reference validation platform. You can see spaghetti of wires, right? Doug is very familiar with this. I know we've worked on these validation boards. So right at the center, you have the CPU, center of the universe, and then GPU. And then you debug it. Eventually, once it's debugged, you take it to closed chassis. It could be a phone, it could be a laptop, as shown below. Now, the middle shows the closed chassis, where you have a closed chassis connector. In the earlier days, this is during Nokia days, I'd like to thank Rolf for his inputs into all this work that I've done. We both were instrumental in bringing USB closed chassis debug. I should have acknowledged his contributions right at the beginning. I have his name written at the first foil. But Rolf Kunis, in fact, I spoke to him yesterday. So we came up with this method. And in fact, some of these figures are from his work that he did at Nokia. He moved from Nokia to Intel many years ago. And extreme right is the wing board. It is in between open chassis and closed chassis. So you have a wing, which is, you see on the right-hand side, it's the debug card. The debug card gets connected to the debugger. So now we've moved on to either open chassis or closed chassis. Now, as I mentioned, closed chassis enables debug without opening the chassis, right? All you do is connect it to the USB-C and be able to debug. Now, keep in mind that it doesn't mean that I can borrow Doug's laptop and connect my debugger and then debug to the heart's content. No, you've got to go through and take care of security disabling, right? And so just to make sure that your secrets are protected, there are keys, and then your personal information, right? Privacy needs to be protected. So all that needs to be protected, and unless you're authorized to debug, you cannot. However, keep in mind that the debug folks, when they get the part for debugging, they have the authorization to debug and they can debug, right? So closed chassis enables you to do hardware, software, and firmware debug. Now, early validation debug on form factor avoids the effects of RF, power, thermals, etc. And sometimes customers use it for mass testing, with hundreds of units being simultaneously tested. It also helps to reduce DPM. DPM is defects per million, right? If you look at most commercial products, it's 400 DPM or 300 DPM. But when you go to automotive applications, they are down to 10 DPM or even lower, right? So the reason is because you don't want your car to not start, right? You got to make sure that the failure is minimized. And it also allows in-field debug to collect SoC platform parameters. What is in-field debug, right? I want to introduce in-field debug here. So imagine you're driving in your automated car, ADAS, right? And you have, if not hundreds, tens of chips in it. I think hundreds is probably true. It's probably true, right? Right from infotainment systems to engine controls to, well, there's no engine, there's motor control in ADAS, right? In electric cars. So you don't want that to fail. So you want to be able to constantly be able to test and debug in mission mode. Yeah, you've seen Waymo cars. You know, Waymo's been, these are automated robo taxis in San Francisco and in Arizona. I sat in one of them. I was really scared, right? You sit on it, you hail a robo taxi, a Waymo, and sit in it, and the car just suddenly turns, you know. When you're driving, you know which way you're turning. So you're prepared. So this Waymo car was like, it'll take you to your destination. But, you know, I was so scared of sitting like that. Exactly. But that's going to be the future, right? Tesla is going to bring robo-taxis pretty soon, I heard. So in-field debug is becoming very, very important. In fact, ITC called me and said, Sankaran, can you prepare a tutorial on in-field test and debug? So these days I'm preparing a tutorial, which I'll be presenting at ITC this November. So again, in-field debug, you need a connector. The connector is USB Type-C, right? Best thing since sliced bread. So connector of choice is USB Type-C. Moving on. Now, I want to get a little bit details on how the Type-C works. I talked about host role versus device role, right? So I mentioned that when you say on the go in USB means that on your laptop, your USB-C can be a host or a device. In the sense, I can get the pictures in my laptop and send it to my printer or a hard drive. Or I can take pictures from my hard drive or a camera and bring it back into the laptop, right? So it's both host and device. Now, a printer is purely a device. So if you have a USB-C connector there, it works as a device. Now, how does it know that it's device or host? So it's all through resistors. We have to go back to our electrical engineering basics, right? You have these resistors that are connected. So now there's something called DFP, which is downward facing port. Imagine a stream, right? You have downward facing. So this is a host. And you have upward facing, upstream facing port. That's a device, right? You're sending from host to device. Now, a laptop could be host or device, right? Now, host is connected by, you see DFP. When you have the resistor RP and this side is open, then it's a DFP. DFP is downward facing port, which is a host. And on the other side, you have UFP, which is upstream facing port. You have RD and open, right? So RD is pull down, RP is pull up. Pull down, pull up. And this is how you determine whether it's host or device. Now, what is DRP? The one on your laptop, this is DRP. In the sense it's dual role port. It can be UFP or it can be DRP. Now, what does that mean? It toggles between RP and RD. It keeps toggling at a certain rate. Now, the moment I connect a device, and if the device turns out to be a host, it says, you connected a host, I'm going to become a device. And it keeps toggling. If I connect a printer, it says, you connected a device, I'm going to become a host, right? So that's how you decide what you want to be. Okay.
So you said the device is always, can you go back to please?
Sure. Pull down.
So the device is always a pull down,
Right.
which is EFP, downward face,
No, UFP. Upward facing.
upward face, port. Port is upward face.
Uh-huh.
So you have a pull down resistor.
Correct. Yeah, it's a little tricky.
Yeah.
Right.
The
Yeah.
printer can be a host also, right? Smart device.
Yeah, it can be a host also. But he's specifically asking for a
Device.
a device.
Because if an instrument is
Device.
figured in the device mode, then it has to be UFB.
Okay. It'll be RD. Okay. So now, how did we configure it for debug purposes? So you have these resistors for DFP and UFP, and audio has a certain resistor configuration, right? And it's RA and RA for analog purposes, not RP and RD. And so you have alternate mode where you can send a PD messaging and say, hey, change to this mode instead of resistors. We put resistors because you want it to be blind. You take a connector, you want it to automatically, they call it as automagically, right? So automatic, it's automagically configured. So that for that resistors would do. So you have alternate way, which is through PD messaging, power delivery messaging. The other is accessory mode. So what we did was we did using accessory mode, and this is the DFP, RP. You have in terms of USB-C, UFP and DFP are defined here. Debug accessory mode, we use RD. It's not, you have both pull downs or both pull ups, then it's debug accessory. It's a different resistor configuration, right? And the moment I connect debug accessory mode, this guy says, aha, you want to debug me, right? I'm going to go into debug mode. I'm going to configure the SBU pins to be a JTAG. And USB 2 becomes debug class. USB 3 becomes debug class. And if I want to stream data I'm going to stream data through HDMI, right? So all that, when you connect your USB-C, you should always remember, man, all these things are happening behind the scene, right? So, and then audio accessory mode has asymmetric resistors for orientation detection. So here's the audio accessory mode, which is RA. Debug is RD, and RP1, RP2. And here's or alternately, you have alternate mode, which is I can send a PD messaging through a firmware engine and say, oh, I want you to become so-and-so, right? Now, here's the RP1, the DFP, or upstream facing port, UFP. And DRP, this is where it toggles. Right now, if I don't connect anything, it's toggling. The moment I connect it, it says, aha, you connected a display, right? And that's a device. I'm going to become post. So it keeps toggling between the two when it is open. Now, people say that, hey, aren't you wasting power? Power is very, very minimal. Or very, very minimal. So I had the same question. So moving on, here's the debug alternate modes. So debug alternate modes, you can have USB, display, or Thunderbolt. Why do I need display and Thunderbolt? I have trace, right? I have what is known as a trace arbiter. So I have traces coming from graphics engine, from CPU, from the NOC, all that. I need to send the trace to a debugger. How do I send it? My USB bandwidth is not sufficient, right? I get tons of data coming in, trace data. So I switch it to either USB, depending on the bandwidth, or display, or Thunderbolt, right? Or I could use VDM, vendor-defined messaging. Or we can also use NIDENT overlays. USB, MIPI came up with NIDENT. NIDENT stands for Narrow Interface for Debug and Test, right? Which is done by MIPI Alliance. So here's so the way it works is you have the debug and test subsystem. Through the CC1, CC2, the channel configuration, it turns on the Type-C port controller, port manager. You can select the MUX agents. The MUX agent selects the stream engine for connecting the trace bandwidth and sends it to the debug. Right? This is how the debug overlay works. Moving on. Here's the different debug class that you have. So in case of debug class, it requires the DBC, the debug controller. There's another controller like USB controller, a debug controller, which needs to be powered up. It does not require any OS or software support. So there are 4 different ways by which you can get. The USB debug class DFX is to provide JTAG access. GP1 is for kernel mode debug. If you want to do any kernel mode debug, you can do that. Or GP2 is if I want DMA, I want DMA tons of data back and forth, I could do that. Or dbc.trace, and that's providing trace. Similarly, you also have out-of-band capability. Out-of-band, as I mentioned, is through the SBU pins, right? It's out-of-band. It's the GPIO, as you mentioned, Doug. It's also, Intel calls it as EXI. You're familiar with EXI, right? Doug, you must have heard about it. It's DFX extendable interface to provide JTAG access. So when you connect, you can get JTAG access through it, through USB. And it does not require USB controllers to be powered up because it's GPI. And it's useful for JTAG debug. Now you see, right, it is best in sliced bread. Used to think the sliced bread was the best, and now it's USB-C. Now, DBCs are available over USB 2, USB 3, and speeds from 480 megabits all the way to USB 4, which is up to 120 gigabits per second, all in silicon. It's amazing. Where is 10 megahertz, right? Where is 120 gigabits per second? Yeah, we surprise ourselves. And here's the HDI. So this is something which I want to spend a little bit of time. If you look at this blue box, it's the SoC, right? And the bigger light blue box is the platform. Now, inside the platform, I could have many SoCs. In this one SoC, the purple box is an IP. It could be a GPU, and this could be a NOC. This could be a CPU. This could be another USB controller. And all these are sending traces, right? The traces are sent to a trace merge unit. Yeah, like a trace aggregator, right? Or a TMU. And here you have the MIPI, TWP, which is the trace wrapper protocol and system trace module. So this captures it, and you have a funnel. The funnel is connected to a MUX. So either you can send the display data to HDMI or DisplayPort or USB, or you can switch the MUX, and at the HDMI data rate, you can send the trace to a debugger. I can have a bit bucket sitting there. I can capture all the bits, all the traces, and then I can go look at it and see where the failure is, right? So this is a very, very powerful way, and it actually does provide you at the maximum bandwidth of 80 gigabits per second, right? And then you need to find which particular bit is failing when you have 80 gigabits coming out. That is going to be the challenge, right? So we have provided the plumbing. Here's the plumbing, right? Now you go as a debugger, figure out what bits are coming and what is causing the problem, right? So moving on, summary of USB Type-C for debug. Sideband usage pins are used for bare metal access and MIPI I3C. So what is happening is things are moving from JTAG to I3C, I2C and I3C. And CJTAG is another compact JTAG. We worked on it in 2017 or even before that. So it is essentially taking the 4-wire to form 2-wire JTAG.
That's right. One state machine, other devices don't have state machine. That's how the main state machine on the main device.
Exactly.
Yeah, they're called wire JTAG.
Yeah, that's right. You remember that, right? Now, the reason why we wanted to build this 2-wire JTAG is because if you remember, the old phones never used to have USB-C at that time. We used to have the SD card. SD card had 6-bit data. If you look at it's a 6-bit interface, 4-bit data and clock. So differential clock. So what we said was we'll use the 2 pins for JTAG communication and 4-bit for trace. That's where CJTAG was developed. But then right after that, we got USB-C and we said, oh, who needs the CJTAG? We got the best things in sliced bread, right? So moved on to USB-C. Now USB 2 DBC gives you debug class. It is for functional data transfer and for GP1. USB 3 is for super speed and for Thunderbolt or maybe HTI, high-speed trace interface. Then electricals are, SBUs are CMOS or GPIO. USB 3 are SerDes, and USB 2 is in between, 480 megabits per second, right? So here's the debugger sitting there. It has DCI out of band, direct connect interface out of band, which is nothing but JTAG. Then you have DBC, debug controller, and HTI. So it is one ubiquitous connector for closed chassis debug. Okay, so as I mentioned, here's the connector. Type-C connector has USB high speed, which is USB 2, USB 3, sideband usage, CC pins, SBU pins. Actually, I'm going to delve into in-field debug and silicon lifecycle management in a minute. Before that, I wanted to show you, this is your SoC system on the right-hand side, and this is the connector, right? As you saw, the connector is here. It has USB 2, USB 3, then you have display, you have ground and power, and then CC1, CC2, and SBU. Now, the way it is connected is, if you look at the system on the right-hand side, you have the low-speed traces. Low-speed traces are directed to SBU pins, as you can see. It goes to SBU and to USB 2. And the high-speed traces are connected to USB 3 and to DisplayPort. So if you move on, so Type-C connector is connected to the debugger either using a captive cable or direct connect. And connections are made using RDRD, RP1, RP2 over CC. This is to get to the debug accessory mode, right? And you have the PMC controller, power module controller, to do the port mux selection. And you have firmware-based controller to get the subsystem 1. And then you have these switches. You see, 5 is a mux switch, 6 is a mux switch. This is a port controller. Here's a port controller sitting in there, and this is the connector. And once connection is done, SBU pins are used for bare metal debug. USB 2 and USB 3 are made available over the respective pins, and display port for high-speed traces. Moving on. What about customer platform debug usage? You want to have ease of diagnosis of customer platforms, right? The goal is to observe, analyze, and optimize the products. What is the customer expectation? Customer would like to have effective, robust, consistent, easy-to-use solution requiring no platform support, right? So customer says, I want you to give me everything, the complete solution, without any expensive hardware. And that's what USB-C provides. And it also provides ease of closed chassis debug and analysis. Yeah.
So on the debug target debug test system on the left side,
Uh-huh.
what is the software that is running to enable any traffic between those two?
So that is the debug software that
Comes with who and
comes. We have a debug tools team, debug tools team. I don't want to name names because I know the name of the person at the top. Right. They develop the tools. And then you have the users. We provide the hardware architecture.
Okay.
And the debug tools team says, oh, here's the JTAG driver. Here's the USB 2, USB 3, tool, which will extract information for you.
So it's one of the debugging hardware components that will run that software is that Lauterbach?
Lauterbach is one of them.
Yeah.
Very good point. Doug is, yeah. So Lauterbach is a external debug vendor. In fact, Rolf is at Lauterbach. If you have any questions, you can contact Rolf. And I'll show you some of the connectors, cables that Lauterbach provides. I'm not done yet. I still have a few more foils for Lauterbach. Does that answer your question?
Yeah.
Yeah. So Sharath, that is a very good question. Going to the next one, security implications. Now, closed chassis debug, right? It actually, people think that it's wide open, right? Open for all. Anybody can go in and debug anything. In fact, there is an organization called Black Hat. All they do is hack into computers, right? So Black Hat, in fact, DFX port, right? It's all through DFX port. Designed for test, designed for debug. X is your favorite alphabet, right? You can T for test, D for debug, M for manufacturing, Y for yield. That's why the X. So this DFX port, what happens is you, in your home, you close all your doors, all your windows, and you keep a sliver of window open to get some breeze, right? So DFX port is like, it's a most vulnerable port on a device. Everybody's trying to hack through the DFX port because you want the DFX port to be open so we can do debug. But you want it to be closed so that crooks cannot get in. Hackers cannot hack into the system. But it's like a cat and mouse game, right? The hackers are trying to hack into it, and the designers like us working for a company are making it stronger and stronger to not. But these people are always trying to find ways to get in, right? So Black Hat, they actually went into the hack and turned off the computer running unsigned code in Intel Management Engine. So Intel had to plug in that hole. And then there is a debug capability called Visa, right? Which most people know. Based on NOAA, Node Observability Architecture, which became virtualization of internal signals architecture. And they found a vulnerability, right? So, but it's been closed. It's been closed. It was not easy for them. It is roundabout, but they couldn't hack anything personal or secure information. So right now, I think every port has to have has to be made secure, right? Based on security authentication. So I just wanted to mention that no port is secure, but you have to make it secure by design. Otherwise, very vulnerable.
So if I were to give a phone to some debug guys,
Uh-huh.
so the debug guys should know what the security is this, and they go through some security authentication before they get inside
Yes.
the handshake.
So
So
it,
the debugger has to know what kind of information.
exactly. Exactly. So you know it's an Apple device, right? Or a Android device. So they all have different debuggers. So you try to interchange it, it probably won't work because they have their own protocol to even talk to each other. You try talking it, it'll shut itself off. Right? So
the debug host has to know how to get inside.
yes. Yes. It is not that simple. Even if it's a Intel device, you have to have the authentication. They have a secure server sitting at Intel, which says that I'm going to open the device for X seconds just to get this packet. So it's all logged.
Yeah.
Yeah. It's all there.
So that server host, if I remember right, is the secure unlock, like when you're
Secure unlock.
Secure unlock.
Yeah.
It allows you to get the fuses and everything, but you have to do that first.
Exactly.
Yeah, I remember seeing some of the engineers, they take the blue box or something, I forgot.
The blue box. Yeah.
Yeah, they used to take it to the customer side if they have an issue, and then it sends an authentication to the Oregon servers
Exactly.
and authenticate and all that stuff.
Yeah, folks on the bridge, what Sharath is saying is that you have this blue box, and if you take it to the customer side, you have to authenticate with the company's server, and they have to give you permission to debug.
Yeah,
Otherwise,
that's
you cannot.
the endpoint.
Exactly. Employees have to take it and go there. Absolutely. Yeah. So it's not free for all, right? So it is very, very secure. You have to make it secure. Otherwise, you have these stock codes, you have privacy information, you have secret keys, right? All that. And then you have fuse. You can actually,
That's right.
yeah, people have done voltage hack, right? You can actually hack into and increase the voltage and destroy the chip. Right? So there are ways by which the chips can be destroyed. Chip can be compromised. So there are side channel attacks that people are trying, right? So yeah, I hope people use smarter ways to develop smarter things rather than coming ways to destroy a chip, right? Okay. Okay. So overall debug of SoC. Closed chassis is also useful for in-field debug. And another term that I'd like to use is silicon lifecycle management, right? So if you look at the box on the right, I am showing the SBU pins, the channel configuration pins connected to Type-C USB and connected to the debug host. And you have all these PMC, power management controller, and the port controller, which does the muxing. A lot of background information goes on before you can access the debug. I promised you that I'll talk to you about the different connectors that are available. So especially, Doug, you mentioned about Lauterbach, right? So at the top, you have this USB-C to USB-C. This is NVIDIA Orin GPU, which is using a USB port switching. So even though you're hearing the USB Type-C for the first time, USB Type-C has been used for debug for ages, for the last several years. We standardized it about 8 years ago, and it's being used by almost every company. Here's NVIDIA's high-speed test protocol and debug and trace. Then you have device USB connection that is shown here. It's a 40-pin Samtec connector, USB to USB. And here's the Lauterbach connector. This is the target adaptation for converting the 40-pin HSSTP to USB-C. Let me show you a few more connectors. Here's the Lauterbach HSDP high-speed data port adapter for power trace serial. This is USB to USB-C breakout. And this is the combi probe for DCI out of band. This is for out of band is for JTAG, right? And then here's the USB debugging, full USB debugging, right? So you can get not just JTAG, but also trace, USB 2 and USB 3, right? And then here's Apple. Apple uses their Bonobo. This is in the public literature, right? Bonobo JTAG serial wire debug. Apple introducing the USB-C diagnostic tool. Then you have Google Chrome using the sniffing dongle, supported by Chrome devices. This is they call it as case closed debugging debugger or closed chassis debugging debugger. Right? So all these are available. And then here's the Mino USB-C DAM. DAM stands for debug accessory mode. Don't get me wrong, not the damn chip, right? It's debug accessory mode. It was fun when we came up with this DAM. Doesn't have the N in it. Okay. And then USB Armory MK2 debug accessory. And this is the TI debug accessory mode. So everybody is using USB-C for debugging. Now here's in-field debug. I briefly touched upon it in the past. In-field refers to the process of identifying and fixing bugs in a live system. Like I mentioned to you, you have ADAS, right? Automatic driving. You have system running in mission mode. And you want to be able to, you cannot afford to have a catastrophic failure in a Tesla car or a space vehicle. Space vehicles have TMR, right? Triple modular redundancy. So instead of one computer, they have 3 computers, right? And then they have a majority voter. And if, assuming that one of them fails, the other 2 gives you the right results, right? But for commercial purposes, I don't think Tesla or any EV can afford to put 3 computers instead of 1. Becomes too expensive, weight becomes high, costly. So now whatever you build has to be really, really reliable. And if something is going to fail, you want to be able to find out when it is running. So I have a patent which I wrote, which has been granted, where for in-field debug, what I said was, when the system is running in mission mode, take it out of mission mode, cycle steal, run your LBIST, run your MBIST, get the results. If it's passing, move to the mission mode. So you cycle steal between mission mode and, right? And I don't know why somebody didn't think of it. Probably I thought of it first and the patent got granted, but there's more to it. It's a very simplistic way that I'm explaining. There's a lot of math that I added to it to make it more robust. So that is what is in-field testing. And in-field debug is the same thing. You not only have to be able to find out what is wrong, whether something is failed, but also find out what is wrong. Now, the other thing that I'm working on is known as self-healing.
Yeah, in-field repair.
In-field repair,
Yeah.
right? In-field repair or self-healing. In the sense you get hurt, the skin gets cut, within a few days it heals itself. Why can't we do it on your chips? Something fails, you try to find a way to find an alternate path, right? Like doing a bypass surgery. Again, medicine, right? So we take everything in detective or medicine, try to apply it in debug. So this involves analyzing hardware behavior by periodically real-time testing, right? That's what is in-field debug. And do adjustments on the fly while the system is running. And then you have in-field debugging requires diagnosing hardware or software issues while maintaining system availability. You can't take the system off of mission mode, but you can do cycle stealing in between to find out if something is wrong, right? Then conventional debug methods interfere with the performance. So we got to find out using closed chassis to do in-field debug. Now, security authorization, we cannot forget security. Now, here's lifecycle management. Every company is interested in silicon lifecycle management, right from architecture to SoC design, to validation, to manufacturing, to test and debug, to in-field debug. Now, what they want to see is, they want to see how the system is progressing, how your clocks are behaving, your duty cycle is behaving, how the system is functioning, performance monitoring. And then when it goes into the field, each of these chips are ID'd. They have a fuse which tells you what is the ID number. They want to be able to track how the system is behaving after 7 years. How much has it degraded, right? If it has degraded, can you send a signal to add some more allowance to make it better, right? Like a brand new chip. So silicon lifecycle management has become a big thing. Synopsys is working on it, and many other companies are working on it. So I've got a couple of papers on. So what they want to do is, if you look at my last bullet in this foil, it enables capturing information right from manufacturing all the way to end of life. We call it as cradle to grave of a chip. You want to be able to monitor right from the beginning. You start manufacturing it, designing it, manufacture it, put it in the field, all the way. Then you say that, hey, I'm decommissioning this part after 7 years or 15 years, right? How did it degrade? Is it, I still have, I don't know if you remember the Banyas computer, your Marom. It's the very first low power chip that Intel made. This is like 20 years ago. It still boots. I have it at home. 20-year-old chip, right? But it's very, very, very slow because it's like a 25 megahertz system. So imagine it's so reliable that even after 20 years, it still boots. So that's the lifecycle management that people would like to look into. And then P2929. This is a little bit of sales pitch. I actually chair the standard. If you're interested, please do join. Essentially, what it is you're familiar with scan and array dump, right? Debug. So we are standardizing the way we debug using scan dump and array dump. People don't want to call it as dump, call it extraction, like scan extraction, array extraction. So you connect your debugger, and whether it's a Intel system or Qualcomm system or Apple system, if they follow the P2929 for scan and array debug infrastructure, you can debug it in a uniform way, right? The advantage is that we are working with the big three, which is the EDA companies, Synopsys, Cadence, and Mentor Graphics, which is a Siemens company, to come up with a debug infrastructure so that the price of debug infrastructure becomes cheaper and it becomes standard. It becomes plug and play. You connect it, as long as you know the security authorization capability, you should be able to do JTAG or USB-C debug, right? So P2929, if you're interested, please shoot me an email. Anybody on the bridge, right, on the Zoom call, send me an email and sankaran.menon@gmail.com. I'll be able to add you to the P2929. We meet every Thursday, about 25 different people from different companies we meet. We've been meeting for the last 4 years. As Luis was mentioning, that most standards take 7 to 10 years. In 4 years, we are almost about to wind up. I wouldn't say wind up. It might take another 2 years because, when two people meet, there are 3 ideas. Think about it. Okay, me and Doug meet. I have my idea. Doug has his idea. We both have a common idea. So there are 3 ideas, not just 2, right? So imagine 25, 30 different companies meet. There are like 100 different ideas. So I have to herd everybody and come up with a common. That's a job of the chair, right? I have the responsibility. I have a lot of people who are helping me with that. So in-field test and debug and silicon lifecycle management, all that can be done using P2929. Now, moving on, I want to give you standardization, which took many years. So we started off with first CJTAG, 2004. Then we came up with MIPI narrow interface for debug and test. We published a MIPI white papers, the first implementation, first public spec in 2010, industry standard, MIPI spec was approved. I have a few more things. SVDTC, I need to update this foil. System validation and debug test technology council. And then the P2929 started in 2020. We are in 2024. We want to bring it a standard in 25 or 26. So we have been very busy working. Now, in terms of conclusions and future work, so we have one ubiquitous connector for closed chassis debug. It spans functional as well as debug needs. Debug accessory and alternate modes to cover major debug modes. Debug accessory mode is hardware-based, and it's debug alternate mode way, which is PD messaging. USB 2 DBC and USB 3 DBC for covering low power and high bandwidth traces. Then you have sideband usage signals for bare metal debug. Bare metal is even before you install your OS, you want to be able to debug. Sorry? UFI. UFI debug is another one. Yeah, what used to be known as BIOS is now UFI, right? UEFI. Gone are the days of BIOS, right? Basic input-output system became UFI. Now, closed chassis debug is not only useful for platform debug, but it's also for software, firmware, and hardware debug. Especially useful for over-the-air updates, right? You want to do over-the-air updates and you have any problems, the only way to look at it is using closed chassis debug. Now, OTA or the on-the-air updates are very common for smartphones, IoTs, ADAS, and industrial applications, right? Now, in terms of future work, Before that, it's useful for in-field debug, right, and for silicon lifecycle management. And the capability that this feature provides for lifecycle management is to monitor and extract the SoC parameters, to optimize the platforms, and to capture the information right from manufacturing all the way to end of life, right? As we call it, as cradle to grave for SoCs and platforms. So you see the medical equivalent of this, right? Cradle to grave. To enable lifecycle management, traces to be sent to the cloud. Now, the future work that, I shouldn't say future work, the Bluetooth connectivity. On the right-hand side is the target system, device under test. On the left side is the DTS. We did come up with a Bluetooth way of testing it. And we were able to, the Bluetooth, the only thing is that it's very low bandwidth, right? So we're moving to Wi-Fi, which is much higher bandwidth. So, but even low bandwidth doesn't matter. Debug is done very slow, right? You're not sitting there and debugging like that. No, you get the trace, you sit on it, you analyze it, you find out what is wrong. So slow speed doesn't matter. It does help. Now, thank you very much for your undivided attention. I'll open up for Q&A.
We have security issues, right?
Yes.
So you have to somehow encrypt or do something.
Yes. Very good point. Louis brings up a very good point. He said that Wi-Fi and Bluetooth could potentially cause security issues, right? So you have to make sure that once connection is established, everything behind the JTAG needs to be secure, right? So again, you have to have the authentication done before you can proceed any further after the initial connection.
So, Sankaran, I mean, almost your entire presentation is all hardware.
Yeah.
I mean, you touch on, obviously, you have a lot of software that is to work with this.
Yes.
So I guess there's a big team of software guys, because you have to write the apps and the software to support all this debugging.
Exactly.
So like, I don't know if you want to comment on how big the team is. There may be even separate companies providing this kind of software too, right?
Exactly. Very good question. So just to repeating the question for the folks on the bridge. So Lois's question is that, I covered mostly hardware, and for all this to work, there's a huge software and firmware requirement, and there are teams. So to answer your question, Lois, there's a big debug tools PDA team developing the tools, not just software, but firmware too, right? And for some of the applications, we actually go to external vendors like Synopsys and Cadence and Mentor. Yeah. Any question on the bridge? I know we are.
Is there questions, but I can't access it for some reason.
Oh, okay. Sorry. Okay, no questions. Okay. Any other questions from the audience?
Yeah, thank you very much.
Thank you. Thank you very much. You've been very patient, and I hope you understood and you realized it's best thing since sliced bread. That's one takeaway I'd like you to take away from this talk.
Very interesting online, very interesting, and thank you.
Oh, thank you. Thank you, Terry.
And on behalf of IEEE,
Oh,
thank you for your presentation. I will present you this highly sought after
cup. Okay, I will share this in the bridge. Louis presented me with this cup. Thank you very much. I will save this for eternity. I love an IEEE cup.
And if you break it, I have another one.
Oh, thank you. I'm looking forward to the IEEE life member, because I've become a life member.
Yes.
A shirt.
You not already. You may be close to it.
No, I'm a life member.
You're not.
I'm already a life member. Only thing is I need to become a active.
You can be we can talk about being an officer.
Oh, okay.
Then you can get this nice shirts too.
A shirt too. Yeah. Thank you.
Chair,
Okay.
Always for a few more months.
Okay.
Welcome, anybody who want to join us. On network or the line member, we hold.
Ah,
Plus, work experience.
I'm not old. I'm still a life member.
Turned on his video.
Okay. Hi, Tom.
No, I guess not.
Okay, I'm about to.
Okay.
Yeah,
Tom, you want to
all.
say something?
No, just,
Any
I'm
comment from the audience?
a little
I
concerned.
think Tom was saying something. We can't
Tom,
hear him though.
Tom, you're off.
Hello?
Tom, I cannot hear you.
Just shut up. Oh, okay, yeah, but we want to keep track of everybody. Then there actually no requirement. Attention to it, and yours, man, so just there are costs count open, so you come one more time and get all of that. Then I would probably to get your right who's already so yeah, awesome.
So do you meet once every month?
Once a month.
Once a month. When's the next one?
It's always on the third Thursday, like of the month, unless we change it.
Oh.
Most of the time, it should be on the third Thursday.
Third Thursday. Okay. I'll make it a point to.
Well, sorry about the background noise. Any question from the audience? Tom, we cannot hear you.
Every time this on for a few seconds.
Yeah, to turn up.
They did this little.
Without believing.
Okay. Turn off the fan.
A little bit
But
better.
Tom, you kind of,
Oh,
your signal's off.
now it's a lot closer.
Okay, we turn on the fan. So anybody have a question, please ask or raise your hand.
You can raise your hand if you have any questions.
Okay, if not, we'll open the speaker. Sankaran, for quick talk. So I learned a lot about product engineers. I did not do any particle test.
Okay.
Presentation about, USB to function. First, I thought that can go in both sides.
Yeah.
Lightning.
Lightning connector. Yeah.
But you do a lot more. But looks like there's a lot of pins, about 20 something.
Yes. Yes.
I mean, also USB only 4 pins, right? Or-
Yeah. USB only 4 pins, but it gives you a lot more capability. And even the connector is much smaller.
Yeah.
So small.
Yeah.
Yeah.
All right.
A lot of advantages.
Yeah. The thing they kind of flip.
Yeah. You can flip it. Yeah.
And we see at the same time.
Right. You can transmit, you can receive, and it's a host device. It's on the go. It does power delivery, right? Power.
Yeah.
That's the biggest advantage. Yeah. And it's a standard connector. Exactly. Yeah. And if you have power, you can use it to drive it can be used as exactly. Okay. Thank you very much. And I'm going to disconnect the Zoom call. Thank you very much for joining.
Yeah.
You all take care. Have a nice rest of the evening. Bye-bye.
For the rest of the audience, we'll have a meeting in October 19 or 17. The topic is engineers contribute to World War II, right? And November, December, I have a meeting, but a lunch. So just kind of look at our announcement. Right? So I'm going to close the meeting. So see you guys.
See you then. Bye.